name is Ronnie Stern, for those of you who don't know me. And I wanted to thank the organizer, but specifically Victor, for arranging time so I can be first, because as Erez said before, I will have to leave in about an hour or two, so for personal reasons. But I'm still very happy to have the opportunity to tell you about this work. This is a research project I've been working on for the past 1.5 years, a bit more. And I mean, the name is a bit long. It's a system for lifelong resilient job shop planning based on learning machine capabilities from operational data. But it's really a step that we're doing towards trying to build a smart factory that is resilient and can work really all the time and fix itself. This is joint work with Lara Crawford, Victor Piotrowski, and Michael Youngblood. You can see the pictures there. You don't have my picture because you can see me now. It's a research funded by Xerox. And you can understand also what's the motivation. I mean, Xerox has many factories around the world. So and these factories produce printers and material. So obviously they want to automate that process as much as they can. Yeah. So before I start, I do want to make a disclaimer. So this is a work in progress. So you will not see here experimental results showing. I mean, we've built a system, but we don't have yet a nice experimental results where we compare different things. So really, it's a work in progress. That being said, we do have a patent on the architecture. So I mean, it's not. I mean, I do have something to tell you that I think is worthwhile and fun. So what am I going to tell you? So I'm going to tell you about this AI that we've been building, and it's able to learn from observing operational data of machines in a factory. What is the machine's capability, and then it uses that capability models to plan the activities of the factory. Specifically, it's a job shop, so we have parts and you need to manufacture them, and to manufacture them you need to allocate tasks to machines. So we do this planning based on the learned capabilities, and then we monitor the execution and we detect failures when we see them, and when we see failures we diagnose them and adapt accordingly our capability model. And I want to highlight two things. I mean, I'm saying we do this, it's not deployed yet in the system, in the world, but we have run it on simulations. So that's one thing I wanted to highlight. It's just not just words, it's really something we implemented. But then second thing is that, so when something fails, our assumption is that when a machine has a fault, I mean, there is some gap between the time you can replace the machine and the time the machine is still there. And when the machine is faulty, if it's totally broken, okay, then it's useless. But there are cases where it's not broken completely, it's just its capabilities are now degraded. So, and we really want to know what type of jobs can we still send to that machine and use it, and what types of jobs, I mean, that machine can no longer do. So that's the adaptation part that you see in the fourth bullet. Okay, so let me introduce some very simplistic terminology. So our job shop, our factory has jobs that it wants to do, producing some parts. So to perform a job, we need to perform a sequence of operations. Operations are being done by machines, but in order for an operation to be done by a machine, each operation has some requirements to allow you to run it. And machines, on the other hand, have capabilities. And if you want to have an operation running a machine, the machine's capability needs to fit the requirements of the operation. Okay, so this introduces, I mean, the first challenge this kind of setup introduces is let's call it the traditional challenge of job shop, which is how to allocate jobs to machines. So when we allocate a job to the machine, we want to make sure that all the operations in that job can be done by that machine. It's true that it might be possible in some cases to have a job move between machines. In this case, we chose simplistic model, but nothing would change if we had if we would enable also to perform different operations of the same job in different machines. It would be the same thing. This is just our implementation for now. So it's really just the implementation detail. Obviously, a plan is if you plan to allocate jobs to machines that don't have the suitable capabilities, it would not be a valid plan. So we want to find valid plans. So that's the standard challenge of job shop planning. There are many objective functions there. You want to maybe minimize the make span, maximize utilization, and so on. That's challenge number one. But it's often the case in the real world that you don't know the capabilities of the machine. which raises challenge number 2, which is how do we assign capabilities to the machine, what every machine can do. So you might say the machine has a manual, and the manual tells you what the capabilities of the machine are. That might be true, but then one thing is that writing the manual's capability in a formal planning language, that takes time. It takes time and effort that you often don't have. But in addition, even if you have done that, machines over time, their capabilities get degraded. So even though initially maybe you had a model of the machine's capability, this doesn't mean this is the current capabilities of that machine. So this is really something that you would want to somehow learn in some way. So the second challenge is that we want to learn the capability of a machine based on observation. In our case, observations, these are operational data we get from looking at the machine executing. So most machines has some kind of logs that they output and some sensor that you can apply to then track some values that describe how that track the operation of that machine, and we use that to try to learn the machine's capability. So now once we do that, we want to try to show that this works, right? Because if we want to deploy this, we really want to demonstrate that this is working, which raises a third challenge. I mean, no one would give you a factory, go play with it, even though, I mean, this project has been done at PARC, at the Palo Alto Research Center, which is a sub-company of Xerox, and Xerox has factories. Still getting to deploy this in a factory would never work unless you first show that it works in some simulation. And surprisingly enough, there aren't easy to obtain factory simulators. And even if we have, they're not necessarily the simulator that you would want to use that are similar to the factory that you want to deploy in. So a third challenge is how to we simulate a factory, again, trying to do that based on real factory data. And this means simulating the type of jobs that this factory usually performs, and then simulating the execution of these jobs on different machines. Also worthwhile because we want to build a resilient job shop planner, then we would like also to simulate faults in some meaningful way. And the last challenge, and really that's the last one, is doing this resilience, which means that we would like to monitor execution, and then if something fails, to diagnose these failures and adapt capabilities. And now I'm going to amaze you with my PowerPoint skills. Prepare. Boom. Okay, so this is we allocated an operation. It failed on some machine, so we want to detect when that happens, and then diagnose why this happened, what's the root cause of this failure, and then update the capabilities of that machine to reflect that this operation can no longer be applied into that machine, and then repair, and then to model what kind of things need to be done to repair that machine, for example. Okay, so these are the challenges. Now our approach to address these challenges, I mean, I would say none of its individual components are particularly novel, but the combination is, in my opinion, is novel. So the first part I already told you about is to take operational data and use that to learn a capability model. So this is a model that for every machine tells you what it is, what are its capabilities. Then we use this capability model and we compile it to a PDDL-based language so that we can run our planner on it and then plan how to allocate jobs to a machine based on their capabilities. So this is the first component of our AI agent. Now to demonstrate this, we take another part of the operational data, which is of course should be separate from the first part, and we use that to create a demand simulator, which is something that outputs a sequence of jobs the factory needs to be produced, and we do that based on just sampling the past data and assuming that the demand that in the past for parts would be similar to what would happen to the kind of demand we'll see in the future. Then we use that to start to build our factory simulator. That's the first component of that, and we use the demand simulator to start feeding it to our planner to then start to simulate the overall architecture of sampling a job to produce, then passing it to the planner to then that would output then a plan of which jobs to allocate to which machine based on the capability model that it has gotten. Then we want to also simulate execution. So we also use that based on data, and our approach to that in this, at least so far in our implementation, was a playback kind of simulator. So when you execute a job in a machine, then we look at past executions on that machine and try to output something that is similar to output this data series of the operational data that is similar to what we've seen in the past from that machine for similar jobs. So we feed that to the planner, and then we can simulate the execution of the outputs of that machine when we perform these jobs. Okay, then we pass that to a fault detection, which will detect if the execution suggests that something has failed, and if it has, then we feed that to a diagnoser, a model-based diagnosis algorithm that is based on the capability model that we've learned, and then that diagnostic would output modifications to the capability model. So then, when we simulate, when we generate new plans, they would not fall into the same pitfall of these of the observed fault. And just to show you how it would work, then a demand for producing some job would come from the simulator. The planner would plan it, simulate, fault detect, and diagnose accordingly. And this would continue. So the idea is really it should be lifelong, and new demand comes, new fault, and everything. And of course, it doesn't have to be that there is fault. Maybe there is no faults, and there's no need to diagnose and repair. Okay, so that's the overall approach. And now I want to tell you about our current implementation of this approach. Okay, so we looked for operational data that was out there and available, and happily enough, for iron milling factories, and iron milling is a process used to manufacture wafers, there is available data set from the 2018 PHM data challenge. And that data set that we have there is very convenient in the sense that it's a multi-step process of producing a wafer, a silicon for some chip, and so you have multiple steps, and you know their sequence, and for every observed step we have a multiple time series with 24 different features, 24 sensor readings, if you will, of the machine while it's performing that task. So for every step in the process of performing a wafer, we have a time series with 24 variables that track it. And we even have some failure modes that are reported there, because the data challenge there was to try to detect faults. Okay, so just to give you a feeling of how it looks like, I mean, you can see here the iron gauge pressure, which is one of the 24 parameters, and you see that the different values for different steps in the process, and different lines are different parts that has been manufactured, different wafers. So we use that data, and we made some assumptions. One of them is that the machine capabilities are related to the recipe steps it can perform. That's, of course, I think pretty straightforward assumption. A recipe steps is what we called before operations. So we perform several recipe steps to create a wafer. In previous, so this means to do a job, we need to do multiple recipe steps and allocate them to a machine. Now, in terms of what is the capability, that's a kind of philosophical question, I would say. And our assumption here, the capability of the machine relates to the ranges of value for the different features that machine can achieve when it's working. So a capability in our simplifying assumption so far is a range of values for every feature. And in our current implementation, and it's very, this is very basic. I think it's like a first step in doing this work, is that we learn the capabilities by tracking the minimal and maximal values for every feature. So, and you can see here some example of the kind of data output we look. So these are two different machines, and the different lines, the iron gauge pressure and H-beam voltage and so on, these are the min and max value we've seen in the training data. And then, so that's how we model the capabilities in our machines. Now, how did we do the simulator? In a very, very simplistic way. So to simulate the demand, we sampled jobs from the test set. Again, operation is a recipe steps, and the requirement for doing a step, we looked at the operational data and the min-max values, and we said that was the requirement. We need something that is a machine that is able to achieve these kind of values according to its capabilities. So if this is what we observed over time for a machine, then we say, okay, for a step, then we say, okay, the requirement for doing this step is that the iron gauge pressure is between -4 and 1.1 -1.4 and plus 1.3. And then when we try to simulate the execution, again, we took sampled cases where that machine did this recipe step and then said, okay, this is what it executes. And then faults occur when we allocate a step to a machine that doesn't have the capability accordingly. Okay, so now then we use so this is how we simulate demands and execution. The PDL-based planner, based on the capability model, was also, I think, pretty straightforward in that it's really an off-the-shelf planner. It was fast download, and we compute a set of relevant machines for every operation based on our capability model. So we just look if the operation fits the capability or not, based on the range of values. And then we generated PDL of this form. I mean, do machine X do recipe step Y, and the precondition that the machine is ready and that it has done the previous step. So this is the kind of PDL, very, very, very simple. Again, this is just I would say an initial effort towards this, and then we feed that to fast download, and it output a sequence of allocation of jobs to machines, or more accurately, of operations to machine that implied also the job allocation. Okay, so now comes maybe I think the maybe more interesting part, or one of the interesting parts is the diagnosis part. So again, we try to execute the plan, trying to execute operations in the allocated machine, and then something happened. It didn't fit because we allocated it wrongly, and then we want to find out which capability was wrong. So classical model-based diagnosis is formalized by when the system description and observation is not consistent with the assumption that all components are healthy, and the output should be a diagnosis, which is a subset of components that are abnormal, and if they are abnormal, that explains what we observed. And the standard way, or one of the way to handle diagnosis in the diagnosis literature, is to extract conflicts, which are a subset of components that if you assume they are healthy, then this is already inconsistent with what we observed. Then really, conflict-directed search is probably the most common technique to do a model-based diagnosis in the literature. So in our system, the system description is which operations every machine can do. The observation is the operation that has been done and failed, and the conflict would be operations failed with that machine, although we thought that machine can do it. So to make an illustration, let's say P1 is one of the parameters. The requirement was this range, and we thought this was the capability. If we saw that the machine could not do it, then either some of the sides, some of the ranges were not true. So either this side or this side, but of course there are many parameters. So maybe it's this side or the other side. And the diagnostic challenge there is, I mean, which capability was incorrect and caused the failure? Maybe it's P1 or P2. And also, even if we knew which one, by how much should we decrease its range? I mean, the red part is the minimal part. Maybe should we do more? Again, current implementation is very simple. We try to follow what's called like a minimal cardinality kind of assumption, or the smallest change needed is probably to make this consistent is probably the most likely. That's not necessarily true, but that's a reasonable assumption to make if you don't know anything else. So we chose the parameter that has the minimal one, in this case P1, and then made the smallest change plus some epsilon for both sides, assuming the degradation comes from both sides. And really, this is very heuristic.
Ronnie, you have about 5 minutes left.
Okay, yeah, I'm there.
Okay, great.
So this is the conclusion slide. So I'm spot on, I think, on time. But maybe I will just add one thing. So if you notice here, I mean, I didn't exploit any internal knowledge about how the machine works. If we knew that, say, extracted from some model of the machine, then we can do much better. Okay, so to summarize what we've done, so we proposed an architecture for a resilient job shop planner with these components, and as I've shown, we learn capability from operational data, and in our implementation, the learning was just looking at the min-max value of every feature that machine has been observed performing. Then we compiled these capabilities to PDDL and run an off-the-shelf PDDL planner to plan which jobs to perform by which machine. We monitor the execution to detect faults. The reason faults might occur is because we used a subset of the data to train our capability model, but then I mean, in our case, we added some faults, but in reality, I mean, it might be the case that what it thought was the range was actually not the range because, for example, the machine has degraded over time. So once we detect faults, then we use the model-based diagnosis MBD to diagnose these faults. As I showed you before, trying to analyze which assumed capability is wrong, and then decrease the range accordingly. And as I told, this is work in progress. So there are fancier learning algorithms to use, and there are fancier planning algorithms to use, and there are fancier diagnosis algorithms to use in each of these components. So we really wanted to do a proof of concept. In terms of outlook, what we're working on now, so we're of course performing large-scale experiment and demonstrating the effectiveness of this on our ion milling dataset. But from the scientific perspective, not that experiments are not scientific, but from I would say algorithmic perspective, so it might be interesting to look at capability models beyond parameter ranges. So one approach can be, for example, to cluster the multi-model operational data that we have into clusters and saying that every cluster is a capability. So if your new the required operation, the data it needs doesn't fit into your cluster, then maybe that would suggest that the machine can do it. So that's one approach. Another one is to look at not the min-max values of one parameter, but multiple parameters, and then looking at the convex hull that is created and assuming that that's the capabilities. Then if we have a sequence of operations that are, so in our data set, we had operations and they were already split into recipe steps. But it's often the case in other data sets that we just have operational data is a large sequence, and we need to somehow chunk it into operations. So that's another challenge. There is also, I think, I would say, learning theory question there of what kind of capabilities we can actually even hope to learn, and what kind of structure the capabilities should have. From the diagnostic perspective, I currently assume that we have the operation that has been done successfully and failed. But if you look at a lifelong perspective, then if something was done successfully 1 minute ago or an hour ago, we should weigh how much we consider that information when we choose how to prioritize different diagnoses, which is an interesting challenge that has not been addressed too much, as far as I know, in the diagnostic literature. Also, so if you observe the kind of learning of capability that I've talked about, it's in some sense very conservative. I mean, it assumed some range that it observed, and then if we diagnose a failure, that range would shrink. So this suggests that it would go ahead and shrink all the time until it's nothing, and then we'll have capability that we have a machine that we assume cannot do anything. So it makes sense to maybe do some exploration, and if we have some kind of system, some kind of machine, and its capability has been reduced, we might still try to go beyond that boundary and then maybe refine more its capability model. So maybe adding some exploration in the sense that allocating it to it jobs that we're not sure if it would be able to do or not, to extend what we think the machine can do. Another thing that we're working on now is experiment on other data sets. Specifically, we're working now on a data set published by NIST of a CNC factory, and you can see here some of the parameter values there. In this case, we don't have a given chunking of operations, but still you can see some pattern going there. So some kind of a temporal pattern analysis should be fun to do and allow us to identify what is the capabilities of the different machines. That's about it. I think I'm on time. Yeah, thanks.
Yes. Are there any? So we are right up against the time for the next paper, but maybe somebody has a question. I see Wheeler, you've raised your hand.
Yeah. So if no one else has a question, I certainly have one. So thanks for the awesome talk. It's super cool, smart factory. My sense is that what I was missing, I guess, is I'm not that familiar with literature in this area, so there wasn't much comparison with related work. So is the main novelty the idea that you are really not just diagnosing the model as faults occur by means of like turning off capabilities, but the fact that you're getting so much of the model from experiential data, and the model itself is more complex with these continuous parameters and stuff like that. Is that what you see as the advance and contribution of this work?
Yes, so I think two things are the contributions. So one of them is I mean, there are works on learning action models from data, right? And there are works for using that for planning, but not a lot of work on learning then and using that and then connecting that to the diagnosis. So I mean, a bit of it, it's I don't think if I want to call it engineering, but it's the wrapping everything together. But the second thing is I mean, as you said, so diagnosis is often like on off. I mean, you have capability, you don't have it. And the fact that here it's a range, and that the range gets degraded, yes, that's also part of the contribution.
Thank you.